For this instructional video, I'm going to go over two forces, tension and spring. The tension force is a force that is caused by either a rope or a chain being stretched and pulled taut. It is a contact force. It literally has to touch the two objects on either end. It's actually a uniform force throughout. There are a few exceptions. For example, if a rope is hanging vertically, a rope would naturally need to support its own weight, so the tension would change slightly. Tension can only pull. It cannot push. You cannot push a rope. You cannot push a chain. You can only use them to pull. There is no actual equation for tension. It's solved through Newton's second law. And then the spring force, I'll come back to the spring force in a little bit, but I'm going to go through three examples of tension, and then we can come back to spring. So in this diagram here, we see that there are two ropes connecting to two blocks. One block is 5 kilograms, the other is 8. We have ropes A and B. And your goal is to find the tension in the two ropes. So I'm going to focus on block A. Start with a free body diagram of what's happening on A. There is the force of gravity acting on the 5 kilogram block, so I'll call it M5G. And then there's also the tension from rope B, pulling it down, and pulling it up is the tension from rope A. So the summation of forces on block A will equal 0. It is in equilibrium. The system is not moving. So the force tension A minus force tension B minus M5G is 0. Now there's definitely too many unknowns, so I can't actually solve this yet. That's where block B is going to come in. Block B, free body diagram is a little bit easier. We have gravity, I'll call it M8G, and then tension, force tension B. Just like block A, the sum of forces on B will be 0. It's in equilibrium. Force tension B is positive, in this case because it's pulling the 8 kilogram block upwards. A few things to keep in mind. Notice that tension B is found in both equations. It is going to be equal in magnitude and opposite in direction, satisfying Newton's third law. So the force of tension B equals M8G. For this example, I'm just going to use G as 10 just to make life easier, and I can do this in my head. But for WebAssign, I would still recommend using 9.81 because if you don't, you could end up getting incorrect values. So the force in tension B will be 80 newtons. I can substitute that into the equation A. So force tension A minus 80 minus 5 times 10. Again, I'm using 10 instead of 9.81 just to make the mathematics a little bit easier. And the force tension A will be 130 newtons. Just like every other force, the unit for tension is newtons. Moving on to number 2. Let's imagine somebody's walking a tightrope and they are in the middle of it. So these angles theta shown on both sides are both 5 degrees. Let's assume that our person walking the tightrope has a mass of 60 kilograms. And our goal is to figure out what's the tension in the rope. So even though it's one rope, we are going to treat it as being two different ropes. Fortunately, the symmetry, since this individual is perfectly in the middle, is going to produce a situation where I don't need to really distinguish which tension is which. The tensions in this rope will be equal. So this is 5 degrees, 5 degrees. So the tension vector is mixed between x and y directions. Therefore, we have to break that vector up into its components. Force tension at 5 degrees. So on the x, it'll be force tension cosine 5. And on the y, it'll be force tension sine 5. Same thing happens with the one on the left. It's just that the force tension cosine 5 is pointing left instead of right. The summation of all forces on this individual is 0, otherwise they will fall and die, and well, that would be bad. Taking a look at the x direction, you have two forces in the x direction. The tension force on the right side and the tension force on the left side. And those are both Ft cosine 5. One of them will be positive, the other will be negative. And we see that, well, the x direction just tells us that a number minus itself is 0. So that's kind of boring. The y direction, you have both your tension forces, Ft sine 5. Both of them are pointing upwards, and mg is pointing down. They will equal 0. So I can call this 2 Ft sine 5 equals mg. Or the force of tension will be mg over 2 times the sine of 5. We said it was a 60 kilogram human. I'll still continue to be lazy, calling g 10, 2 times sine of 5. I will need a calculator for this. That'll be 300 divided by the sine of 5 degrees, and that will give me 3,442 newtons. Now, tension, just like normal force, if it's not able to supply that 3,400 and so however many odd newtons of force, the rope would just snap. Example 3. I have 2 ropes hanging in the sine. This rope here, I'll call this rope A. It's 90 degrees to the sine. And rope B here is 30-degree angle with the ceiling. So one of your geometry rules tells you that this angle will be 30 degrees as well. Building a free body diagram for this block. You have mg pointing down. Up and to the right is the tension from B at a 30-degree angle. And directly to the left is the tension from A. We'll have to break up the tension in B into x and y components because it's split between the positive x and the positive y. So in the x will be force TB cosine 30, and then the y will be force TB sine 30. The summation of forces is 0 because our sine is not moving. The x direction, we have force TB cosine 30 pointing to the right and force TA pointing to the left, and that equals 0. I'm left with 2 unknowns in this equation, so it's unsolvable for the moment. Looking at the y direction, I have force TB sine 30 pointing up, and I have mg pointing down. This one is solvable. So force TB sine 30 will equal mg. The force of tension B is mg over the sine of 30. The mass was 15, so 15 times 10 over a half. That will be force TB is 300 newtons. I can substitute that into the x direction. 300 cosine 30 minus force tension A is 0. So 300 times the cosine of 30 is 260. And moving force tension A to the right side, I get the force of tension A is 260. In a situation like this, where you have the block being pulled directly horizontal and then upwards at an angle, it is a guarantee every single time that this rope here, which has the vertical component, will have more tension than the rope that is horizontal. In general, anytime a rope is more vertical than another rope, it will be carrying more tension. And finally, moving on to spring force. Spring force is a little bit easier because the spring force actually does have a formula for it. The spring force is a force applied by, well, a spring. It does not matter if you compress or stretch the spring. If you stretch the spring 20 centimeters, it's the same force applied as though you compressed it 20 centimeters. The only thing that changes is the direction of the force. There's something called a spring constant. The spring constant talks about the properties of the spring. What metal is it made of? How tightly wound are the coils? How many coils are there? What's the radius of the coils? How far apart are the coils from each other? So those are the types of things that would determine a spring constant. Spring force, like all forces, are measured in newtons. Spring constant K is newtons per meter, and delta X is displacement in meters. You'll see that the equation is put in absolute values. That's because we don't really care if the displacement is left or right, up or down. We only care about the direction of the spring force. So we're just going to solve what the magnitude of the spring force is, and then go back to Newton's second law and assign positive and negative as needed to fit our particular problem. So in this example, let's say I have an 8-kilogram block and I have a spring hanging from the ceiling. The spring is stretched 18 centimeters. I put the block on. As a result, by attaching the block, the spring will stretch even further, and now the spring has stretched a total of 23 centimeters. So what I care about is the displacement. Delta X would be 5 centimeters or 0.05 meters. The original 18 centimeters is not accounted for in the displacement. We don't use the 23 centimeters. We would only use how far it's stretched, which is 5. Question's asking, what is the spring constant? So in this particular case, just like all the other examples, your summation of forces is 0. Everything is balanced out. On the block, you have gravity pulling the block down and a spring force pulling the block up. So I am going to say spring force minus mg is 0. So the spring force is mg for this case, but we do have an equation for the spring force. It's kx. I can then solve the spring constant will be mg over x. It should be a delta x actually. So 8 times 10 over 0.05. And you get a spring constant of 1600 newtons per meter.